Hey everyone, Katrina here, and today we're going to go over algebraic versus geometric multiplicity of eigenvalues. Be sure to subscribe for more videos like this. Okay, so this video is a direct follow-up from my other video on algebraic and geometric multiplicity of eigenvalues. However, this video we're going to explore a new example where we have an algebraic multiplicity that is greater than the geometric multiplicity, and we'll discuss what that means about the matrix structure. But before we dive into the example, we're just going to review the definition of algebraic and geometric multiplicity again. So if you've seen this already, feel free to skip ahead and just jump directly to our example, which is tagged in the description below. Okay, so algebraic multiplicity of an eigenvalue is the number of times the eigenvalue appears as the root of the characteristic equation or the characteristic polynomial. So the characteristic polynomial or equation is given by this right over here. So this says that the determinant of matrix A minus lambda I equals to 0. So we can see here that A represents our square matrix, lambda is our scalar value, which is our eigenvalue, and then I is our identity matrix. So an identity matrix is a matrix that has ones along the center and then 0 everywhere else in the matrix. So this is how we set up our characteristic equation. So instead of solving a polynomial for roots of x, for example, like we've done in the past, now we're solving for lambda. So we're going to have to use various factoring techniques like we've learned before. So again, this algebraic multiplicity just tells us how many times that lambda or that eigenvalue appears as the root of the characteristic equation. So if we get lambda equals to 3 twice, then the algebraic multiplicity would be 2. If we get lambda equal to 1 only once, then the algebraic multiplicity for that eigenvalue is 1. Okay, so that's pretty easy to understand. So let's move on and look at the geometric multiplicity. So this is a little bit different. So geometric multiplicity tells us how many independent eigenvectors correspond to each eigenvalue. And in essence, we're basically looking for the dimension of the eigenspace of that particular eigenvalue. So to find this, we have to look for the eigenvectors of a matrix. So we use this formula over here. AV equals to lambda V. So we know almost everything else in this equation so far. So A is our matrix. Lambda is our eigenvalue like we showed before. And the only new thing here is this vector V. So this here, I'm sure you can guess, is our eigenvector. So this is how you see the equation normally. However, when we solve for the eigenvectors, we typically factor this equation. And the first step is we bring everything over to one side. So we've got AV minus lambda V equals to 0. From here, we can factor out a vector V such that we have A minus lambda multiplied by vector V equals to 0. And then we're going to use this equation here to solve for the eigenvectors. So not only is this video a great resource for you to learn about the algebraic and geometric multiplicity of eigenvalues, but it's also a great resource to learn how to find eigenvalues and eigenvectors of 2 by 2 matrices. So it's an all-in-one lesson, so I hope you enjoy. Okay, now that we have the definitions out of the way, we're going to go to our example. So our example, the question here is we want to determine the algebraic, I'll just write algebraic multiplicity and the geometric multiplicity of our eigenvalues. So I'm going to write eigenvalues as this epsilon kind of E and then just values. Okay, so that's what we're looking for. We're determining the algebraic multiplicity and geometric multiplicity. So let's see what our matrix is. So in this case, we're going to define A. So it's a square matrix, and we have 1, 0, -1, and 1. So let's just look at our properties here. It's always good to identify what type of matrices we're dealing with. So first of all, we can see this is a square matrix. And second of all, we can see that it's a 2 by 2 matrix, meaning that there's 2 rows and 2 columns. So we'll just write that out here. So 2 rows and 2 columns. It's not a symmetric matrix, so I think that's good enough for now for us to define our properties. So step 1 is we want to determine the algebraic multiplicity, right? So in order to do this, we first have to find the eigenvalues. So that is kind of our step 1. So we need to find the eigenvalues of this matrix. So in order to determine the eigenvalues, we need to find the roots of the characteristic equation. Okay, and remember we said we find this by doing determinant of a minus lambda I and setting that equal to 0. So let's go ahead and do that over here. So we have matrix A, so we've got 1, -1, 0, and 1 minus lambda times I. So we said I is our identity matrix. And remember, the size of our identity matrix has to be the same size as our matrix A. So both of them have to be 2 by 2 matrices. So we're going to use a couple of properties here. We're going to use scalar multiplication with our eigenvalue here. So we're going to essentially multiply this eigenvalue into our matrix here. And then the second one we're going to use is matrix subtraction. So as a result, we end up with 1 minus lambda, 0, -1, and then 1 minus lambda. Okay, so now we need to find the determinant of this matrix. So let's just review quickly as an aside how to find the determinant of 2 by 2 matrices. So say we have some matrix B, for example, and it has elements A, B, C, D. So in order to find the determinant of B, we take elements A, D minus elements B, C, and this will yield a scalar value. So now we want to find the determinant of this matrix. Another notation for determinant is absolute value signs. So we can say that we can put absolute value signs around this, or we can just write det of this matrix here, which is 1 minus lambda, 0, -1, and 1 minus lambda. Okay, so now that we have our handy equation over here, this makes finding the determinant actually quite simple. So as a result, we're going to take our diagonal here. So we've got 1 minus lambda multiplied by 1 minus lambda. So that's our AD terms. And then we're going to subtract the other product of the diagonal, which gives us 0 times -1. And remember, part of this strategy is we have to set this equal to 0 and solve for the eigenvalues. So if we go ahead and simplify this, we end up with 1 minus lambda times 1 minus lambda equals to 0, because this whole piece over here goes away. So this is wonderful. It's actually already in factored form for us, so it makes it quite simple to solve for the eigenvalues. So in order to find the eigenvalues, we're going to set each of these terms individually equal to 0. So we get that lambda 1 equals to 1 and lambda 2 equals to 1. Well, that means that it's pretty obvious to see that lambda 1 equals to lambda 2, which equals to 1. So therefore, what do we see? We have a repeated eigenvalue. And so if we recall the definition for algebraic multiplicity, it's how many times does an eigenvalue appear as a root of the characteristic equation. So here we can see that lambda equals to 1 appears twice as the root. So then therefore we have that the algebraic multiplicity is 2. Because it appears twice. Okay, so we have a repeated eigenvalue. That means it appears twice as the root, which means that the algebraic multiplicity is equal to 2. Okay, so now that we have that, we want to determine what is the geometric multiplicity of this. So this is going to be our step 2 here, where we're looking for geometric multiplicity. So if you recall from the beginning of the session, I said that to find the geometric multiplicity, we have to find the eigenvectors. And the geometric multiplicity is how many independent eigenvectors correspond with each eigenvalue, or what is the eigenspace, the dimension of the eigenspace related to that eigenvalue. So we have to use our handy dandy equation, a minus lambda times v equals to 0, where v is our eigenvector. So in order to solve for this, we're going to just do some housekeeping on the side. So we're going to say that our vector v here is equal to v11 and v21 as the two elements. So we're going to call this v1 because right now we're looking for the eigenvector, associated with our first eigenvalue. So we can amend our equation here and have this as lambda 1 and v1. Okay, so we're going to use this over here. So now we're going to set up our equation using linear algebra. So we already have a feeling what this first part over here is going to look like. So we have our matrix A minus lambda. So what is our matrix A again? So we've got 1 minus lambda 1, negative 1, 0, and 1 minus lambda 1. And then we're multiplying this by our vector v1, which we've decomposed into two elements. So we have v11, v21. And the reason why we decompose it like this is so that we can perform matrix multiplication. And then we're going to set all of this equal to 0. Okay? So, let's go ahead and do that. So we can, first of all, plug in our value for lambda 1. So we know that lambda 1 equals to lambda 2, technically, and it all equals to 1. So we're going to plug that in. So as a result, we have 1 minus 1, 0, negative 1, and we've also got over here 1 minus 1. And then we have our vector v11, v21, and this equals to 0. Let's go ahead and simplify this. I'm sorry, sometimes linear algebra is a bit tedious when we have to simplify our matrices, but I promise it's worth it. So we end up with 0, 0, negative 1, and 0 multiplied by v11, v21, and that equals to 0. Okay? So we're going to solve this now. So this is actually good practice for us all to solve matrix, perform matrix multiplication. So just a bit of a heads up, matrix multiplication cannot always be performed. There's certain conditions about the dimensions of the two matrices that have to be met in order for this to be allowed to be performed. So the first thing, or the main thing we have to focus on here, is that the number of the number of columns of the first matrix has to equal to the number of rows of the second matrix. So we can see here that the number of columns equals to 2 and the number of rows equals to 2. So that means that we can go ahead and perform matrix multiplication. So if I were to go and perform this multiplication, what do I get? I get 0v11 plus 0 v21 equals to 0. And I also get that negative v11 multiplied by 0 v21 equals to 0. So essentially, what does that give me? That gives me 0 equals to 0, and v11 equals to 0, because we can divide out that negative 1 over here. Okay, so what does this tell us? Okay, so this is the important part. So this tells us that this equation is satisfied for v11 equals to 0 and any value of v2, 1. Okay, so we can have, I'll just write this out. So v1, 1 is satisfied when it equals to 0, and this equation is also satisfied for any value of v2, 1. So if we were to write this out as a vector, we would say that the eigenvector, so v1, is equal to, let's say, a, or maybe we'll do k multiplied by 0, 1, where k is just any scalar. Okay, so this here is our eigenvector. Okay, so what do we see over here? So we see that the eigenspace related to our eigenvalue 1 is one-dimensional, and that is very important here. So we can say that, so we have lambda 1 has an algebraic multiplicity of 2, because we said that lambda 1 equals to lambda 2, which equals to 1. And here we say, you can see that lambda 1 then has a geometric multiplicity of 1. And why is that? Because the dimension of the eigenspace equals to 1. How can you also see that is that we only have one independent eigenvector associated with, I'll write this out for you, associated with lambda 1. Okay, so this is our only eigenvector that we have over here. We only have one eigenvector. So since we only have one eigenvector associated with that eigenvalue, the dimension of that eigenspace is 1, and as a result, our geometric multiplicity is also 1. Okay, so this is an interesting case here. So we can see that the algebraic multiplicity is greater than our geometric multiplicity. So as an aside, algebraic multiplicity will always be greater or equal to geometric multiplicity. If algebraic multiplicity is equal to geometric multiplicity, then the matrix is diagonalizable. I feel like I might have misspelled that, but so if they're equal, then our matrix is diagonalizable. If not, then we have a defective matrix. So in this case, since our algebraic multiplicity is greater than geometric, then our matrix is not diagonalizable. Okay, so that is the main conclusion that we can draw there. And if knowing that your matrix is diagonalizable has many other implications in linear algebra. For one, you can do like different decompositions, eigendecompositions, and stuff like that, which have their own place and their implications there, which we'll get to in other videos. But for now, I just want you to recognize how to find algebraic multiplicity and geometric multiplicity and understand whether the matrix is diagonalizable or not. And with that, if you enjoyed the video, please drop a like and comment any questions that you have. Another video on this will be released shortly where I'll go through another example and another case. And please subscribe for more fun math videos. I look forward to seeing you next time.